Welcome once again, dear children, to today's topic. Today we are discussing the effect of dielectric on capacitance. So, we already discussed the expression for capacitance of a parallel plate capacitor. In the discussion, we considered two metallic plates separated by a gap. Nothing was there in between the plates and we assumed it to be air. Okay, so in the absence of dielectric, we got that capacitance of the capacitor to be C0 equal to epsilon 0 A by D. Okay, now, so what we have in between the capacitor plates? We have vacuum between the capacitor plates. Then the electric field between the plates, these and all we have already discussed. The electric field between the plates is sigma by epsilon 0, where sigma is the charge density, surface charge density of each plate. One is having plus sigma and the other is having minus sigma. And the potential difference is V0 equal to E0D. So these equations we have already discussed. The only difference is this: we have denoted or used one naught or C0, E0, V0 to show that we are discussing the case in the absence of external, that means in the absence of dielectric. So when a dielectric is introduced between the plates, filling the gap between them, the situation becomes similar to a dielectric in the presence of external field. Did you follow what I said? So we are assuming or we are considering a capacitor, parallel plate capacitor with air first. So there exists an electric field sigma by epsilon 0. And we are filling that gap between the plates with a dielectric material. So the situation becomes similar to what? A dielectric kept in an external electric field. Here, how comes that external electric field? That electric field is produced by the plates. Okay, what is the electric field? Sigma by epsilon 0. So the situations become similar to a dielectric kept in an external electric field, which is sigma by epsilon 0. So the diagram is shown here. You have the two plates with the positive charge density and negative charge density, and in the gap you have the electric field sigma by epsilon 0. It was already there. The shading with the pencil shows that the gap is filled with an dielectric. Okay. Now you know when a dielectric is kept in an external electric field. Do you remember we discussed in the class, in one of the classes, when you keep a dielectric in the presence of electric field like this, you will have a surface charge density. So this is the direction of electric field. So you will have a surface charge density minus sigma p on this surface and plus sigma p in this surface. We have already discussed the polarization of dielectric in an external electric field. The same thing happens with this dielectric also. You have a dielectric in between the gap between the plates. Okay, so since there is an electric field, that electric field causes polarization in that dielectric. Because of that polarization, there will be a surface charge density minus sigma p on the upper plate. This is the way, no? From where it starts, left to right means left side you have minus sigma p and right side you have plus sigma p. Here top to bottom. So top you have minus sigma p and bottom you have sigma p. So this minus sigma p and plus sigma p is the field due to that polarization because of the presence of that dielectric. So here effectively the charge on the capacitor plate, the charge density on the capacitor plate decreased. You look, it was plus sigma, then along with that minus sigma p also came. So what is the net surface charge density now? Sigma minus sigma p. On the upper plate it is sigma minus sigma p, and on the lower plate what is it? Minus sigma plus sigma p, that is minus of sigma minus sigma p. So here we have plus or minus sigma p as the surface charge densities on the upper plate and lower plate. So here also the field is directed from top to bottom. Okay, but the surface charge densities got reduced. So now the net surface charge density is plus or minus sigma p. That means the upper one is having charge density sigma minus sigma p, and the lower one is having minus sigma plus sigma p, that is the same as minus of sigma minus sigma p. Or effectively we can say now the surface charge density is plus or minus sigma p. What is sigma? It was there without the presence of dielectric. Now with the presence of dielectric, due to polarization also surface charge density arises, and hence it changes like this. Now we need to get what is the sigma minus sigma p. Okay, so we already discussed in the absence of dielectric, the electric field was, so this equation 2. Okay, electric field in the absence of electric means dielectric, electric field is sigma by epsilon 0. That means surface charge density by epsilon 0. So now when the dielectric is kept, then that time surface charge density became sigma minus sigma p. So what will be the new electric field? The electric field becomes E is equal to sigma minus sigma p by epsilon 0. So with the 0 suffix we denoted the cases in the absence of dielectric, and the other ones it is in the presence of dielectric. So in the presence of dielectric, electric field becomes sigma minus sigma p by epsilon 0. So what will be the potential difference between the plates? The potential difference between the plates, it becomes V is equal to E into D. That is sigma minus sigma p by epsilon 0 into D. Okay. Now our aim is to find this sigma minus sigma p. So for linear isotropic dielectrics, sigma minus sigma p is proportional to sigma, or sigma minus sigma p is sigma by k, where k is a constant of proportionality and it is a characteristic of the dielectric medium. Okay, and you can say, see, we wrote sigma minus sigma p is proportional to sigma. Which one is greater, sigma minus sigma p or sigma? Sigma is greater, isn't it? So what about the value of k? We wrote k in the denominator. So what about the value of k? K should be greater than 1. So that's what. K is greater than 1, and this k is called as the dielectric constant of the medium. So what is our important equation there? Sigma minus sigma p is equal to sigma by k, where k, the constant of proportionality, is called as the dielectric constant of the medium. Okay, and that what about the value of that k? K will always be greater than 1. So now we are substituting this sigma minus sigma p in equation 5. So we will get V is equal to sigma by k epsilon 0 into D. Now we substitute for sigma. What is sigma? Q by A. So Q by A k epsilon 0 D. Now the capacitance in the presence of dielectric, that means with the dielectric it becomes C equal to Q by V. So substituting for V, we'll have this Q and Q getting cancelled, and C is equal to K into epsilon 0 A by D. So we can compare once again. In the absence of external field, we got C to be equal to epsilon 0 A by D. Epsilon 0 A by D. Okay. In the presence of dielectric, what is the expression? K epsilon 0 A by D, where K is the dielectric constant. So in short, we can say that the capacitance of a given capacitor, for a given capacitor, its area and separation between the plates will be same, no? So for a given capacitor, its capacitance increases with the introduction of a dielectric, and the capacitance becomes K times the previous one. That means, or we can write that equation, C is equal to KC0, where C is the capacitance in the presence of dielectric and C0 is the capacitance in the absence of dielectrics. So for a given capacitor, the capacitance increases K times with the presence of dielectric, where K is dielectric constant. Okay, so anyway, with the presence of dielectric, the capacitance is increasing. Okay, and in this equation, this product, K into epsilon 0 is the permittivity of the medium. Epsilon 0 is the permittivity of free space. So, K epsilon 0 is the permittivity of the medium. That is epsilon, or we can write epsilon equal to epsilon 0 K. And we know for air or vacuum or free space, we say in that for such a case K will be equal to 1 and epsilon will be equal to epsilon 0. So this condition also is there, that is vacuum or air or free space, K will be equal to 1 and epsilon will be equal to epsilon 0. So K is a dimensionless quantity and K is equal to epsilon by epsilon 0. And you have studied already this epsilon by epsilon 0 by some other name in the previous chapter. What was it? Relative permittivity. So K is otherwise called as what? Relative permittivity epsilon R. So K, the dielectric constant, is the same as relative permittivity epsilon R. Okay, so that's what our conclusion. So, by dividing equation 7 with equation 1, we'll have C by C0 equal to K. Another expression for this K, that K is the same as epsilon R, the relative permittivity. So, we are combining all the expressions. So, K is the same as epsilon R. That is the same as what? Epsilon by epsilon 0. That is the same as what? C by C0. And that is the same as F by Fm. This is something which we learned in previous chapter. What is F? F is the force between the two charges when there is vacuum. Nothing in between the what charges. Fm is what? The force between the same charges in the same separation, but when it is kept in any other medium. So force in air by force in medium gives you the relative permittivity, or here the dielectric strength. So all these equations, you just relate and study. Very, very important with regard to 1 mark questions, MCQs and all. So study well. So once again, what is the conclusion? When a dielectric is introduced between the plates of a parallel plate capacitor, the capacitance increases. Okay, so if it is completely filled with dielectric, the capacitance increases K times. That means the new capacitance will be K times the capacitance in the absence of external field. Not external field, sorry, in the absence of dielectric. Now, we will discuss example 2.8. A slab of material of dielectric constant K has the same area as the plates of a parallel plate capacitor but has a thickness 3 by 4 D, where D is the separation of the plates. How is the capacitance changed when the slab is inserted between the plates? So, in this question, we have the capacitor plates and the dielectric of same area, but the thickness of that dielectric, it is not equal to the gap between the plates. That is the case. So it's given, it's having same area and only 3/4 the separation is the thickness of this dielectric slab. So you in the gap whose that separation is that D, you have 3/4 of that D filled with dielectric and 1/4 is free. That means free space. Okay. And you're asked to find the capacitance, the new capacitance when such a slab is inserted. So it won't be KC0 because it is not completely filling the gap. If it is completely filling the gap, means it becomes K times the previous capacitance. So here anyway with the presence of dielectric, capacitance will be increasing, but by what factor it increases, that we are going to find. So how will we find the new capacitance? You know, the expression for capacitance we can find using the expression C equal to Q by V. So it is this V which we have to find out first. So the thing is this, V will not be same for the two portions. That means 3/4 and 1/4. Suppose the potential difference between the or across the dielectric, suppose we call that potential difference as V1, and in 1/4 of the separation we call the potential difference as V2. So what will be the potential difference between the two plates V? That V will be equal to V1 plus V2. So it's just like a series combination there. So we will have V is equal to V1 plus V2. Now our case is what is V1 and what is V2. So which equation we were using to find V1 and V2? So here V1 is equal to E1 into that distance. What is that distance or separation there? 3/4 into D. Now the question is, what is this E1 there? What is E1? E1 is the electric field in the place where the dielectric is present. You know, the electric field in the presence of dielectric is sigma by K epsilon 0. So sigma by K epsilon 0 is the electric field in the presence of dielectric. That into how much is the distance? 3/4 into D. Okay, so that is our V1. Similarly, what will be V2? V2 equal to E2 into that distance. What is that E2 there? E2 is in the absence of dielectric. So it is sigma by epsilon 0 into what is the distance? 1/4 of D. So 1/4 into D. So these are V1 and V2. So what will be the total potential difference V? That is equal to sigma by K epsilon 0 into 3/4 into D plus sigma by epsilon 0 into 1/4 into D. Now taking the common terms outside, sigma by epsilon 0 into 1/4 into D, within bracket you will have 3 by K plus 1. Here one 3 is there, here one K, so 3 by K, here nothing, that is 1. Okay, so this is the expression for potential difference. Now what we will have, what we want to have is capacitance. Capacitance C is equal to Q by V, but what is this Q? Q is the same as sigma A. That is sigma A divided by, here our expression is sigma by epsilon 0 into 1/4 D into 3 by K plus 1. Just a substitution. Now this sigma and sigma get cancelled and this 4 goes to the numerator, epsilon 0 also goes to the numerator. So substituting in the equation, we have 4 into epsilon 0 a by d into, because sigma sigma get cancelled, into 3 by k plus 1, that is in the denominator. Okay. Then in this equation, epsilon 0 a by d, that is what the capacitance of the capacitor in the absence of dielectric, that we can write as what? C0. So instead of epsilon 0 a by d, I wrote C0 divided by 3 by k plus 1. K I took as common denominator, as means in that denominator. So 3 plus k by k. Now take that k to numerator, 4k C0 by 3k. So this is the answer to that question. So only this much for today. Thank you.